let us see how we can define our own function to plot multiple time series in a single figure. So to make things a bit quicker, I have started with some code that's already done. I import a couple of functions from pandas, matplotlib, and numpy, and I read some data. And if we have a look at the data displayed here, first 5 rows, we have electroencephalogram in a couple of channels recorded here as different columns, and that's followed by other things in the end, which we don't look at the moment, and we take from that data frame, we take the first 19 columns, which are all electric potentials from the brain, in this case of a child, recorded as a time series, means every row is a different time point. I have also taken 5 seconds of the recording for those 19 EEG channels, and I have converted them to a NumPy array using 2NumPy. So now we have a NumPy array called data. And if we know a NumPy array, we also know how to get the rows and columns of that array. It's got 1280 rows and it has 19 columns. So in order to have a nice plot, one thing we can do is we can just take code from some function that's been pre-written, and in that cell I just copy that code, I run it, and nothing happens. Why is that? Because that code is not script code like we had before, but is a function definition. So we need to see how is a function defined. It starts with def, short for definition, blank, then a function name, here highlighted in blue. In round parentheses, 2 arguments, so that's input arguments, so it requires data and SR. And it finishes with a colon, and then after having a new line, everything else is indented to the bottom of the function. Red means comment, so it's also indented, but it's within triple quotes. Everything that is within triple quotes is ignored, and it's just for explanation of how the function works. So as we can guess what data means, we can also check here in the explanation what SR means. So that second input argument, it's defined as the sampling rate. So you need to provide a sampling rate as a second argument, and maybe you haven't seen it, but I've actually defined it for that EEG. I happen to know that the sampling rate is 256, meaning 256 samples per time unit, which is per second in this case, so 256 rows mean 1 second of recording. And if I say a duration like here of 5 seconds, it means that the number of rows will be 5 times 256, which is just the 1280 that we saw. So once we have defined that function, we can use its name, which is plot series, and we can use that function name to call it and to get it executed. Of course, we need to provide 2 arguments, one of which is called data and one of which is called the sampling rate. And if we execute this code, we can see that works immediately and plots us all the columns one above each other. Our task is now to write our own function that does the same thing. So how can we do that? Our function needs to, of course, have a function definition. So that's def followed by a space. And then we need to give it a name. So what name do we pick? My plot, something as arbitrary. You pick your name. It just needs to be something that is not already taken in another context. So if I call it my plot 1 and I do the round parentheses for arguments, colon, next line, indent. So I don't put any comments in here, we just want the bare necessities. So what do we want to plot? We need to specify. So one input argument that I think will be the same as before is of course data. We need to get some data, otherwise we don't know what to plot. Once we have data, we can plot those data, and you know how to do that. We call subplots, function that I happen to have imported already at the top. And then once we have a figure environment and a coordinate system within that environment, we can use plot to just have a plot of the data. So this is very naive, of course, very simple, but let's just try to do it. So activate the function, run the code, nothing happens. Just having no error message is good news in this case. And then calling the function, which is called, what is it called? myplot1, and offering it some data, which now for convenience happens to be called data. So if we do that, we can see that works to some extent. Well, it does what we asked it to do. It took all the columns of that data array and it puts one on top of the other. So it's nice. We have it horizontally displayed. And we can see some values here for the voltages, and we can see the samples here, 1280. These are the rows that we have provided. So let's be content with that at the moment. Let's not be content with the fact that all columns are plotted on top of each other. How can we separate them? So obviously we need to modify our code, and rather than putting that in here, I just copy and paste it and we expand the code. So let's call this new attempt myplot2, and let's think for a moment what we need to do to get the time series separated such that we can see each one separately. So there's nothing wrong with figax and plot, so we leave all this. How would we separate one time series from the other? So the separation needs to go vertically. So it means to the existing data values, we need to add something, right? So if our first column is plotted on a certain horizontal line, then the next data columns should be either below it or on top of it, but offset by a little bit. So in principle, it means something like adding a number. Right? So if I add 1, it means there will be an offset of 1. It's a stupid offset because it will offset all the data. So there will just be the same plot as before, just on the vertical axis one more. So how can we get an offset that is specific, that goes column-wise? For this, we need to have a function that gives us a set of numbers, each bigger than the previous one. And one of those functions that does this is arrange. So that's array range. That's to deal with NumPy arrays, which is what we want to do. If you don't remember what that does, just give in a number and you can see arrange gives you a range of numbers between 0 by default and the number that you provide, -1. It gives you 10 numbers if you specify 10. So in our NumPy array we have 19 columns, so ideally we would like to have something like this. Numbers from 0 to 18, which means we could sort of offset every column a little bit more. So the first column offset by 0, next column offset by 1, next column by 2, and so on up to 18. So let's try that. Let's try to use this piece of code here to replace that one and say instead of offsetting it by 1, I offset it with a range of 19. And we can test this by now, just make this empty again, by calling that new function, which is called myplot2. And work on the data. So what do I get? Well, not really anything surprising because it looks very much the same as we had before. But if we look at the numbers that we had in our array, where did we see the numbers? Somewhere here. Numbers are 7, 22, 6. on the order of 10 to 20. So in that sense, offsetting it by 1 is just on the order of 10%. So it's not a lot. So how can we offset it by more? So the way to offset this by more is to just multiply it with a factor. So just say take 10 times that number and to just test whether that works. See what it does. Copy the code here, see what it does. And that looks nice because it's now 0, 10, 20, 30 up to 180. So isn't that good, right? So that's somehow what we wanted. And so if we have that 10 times, execute the function, call it, yeah, we can see we're getting there. Slowly, slowly. Let's just change it and let's say 10, maybe it's not enough, do 100. And that looks even quite nice already. Go even further, take 1000. Well, that looks a bit stupid. It's not very nice. It's overdone, right? It's too much. So let's just not do more experiments. Let's just stick with this number 100. That seems to be quite okay. So that's a good function. It does what we want, but it doesn't do it in a generic fashion. What is non-generic? First of all, the 100 and then the 19. So let's address them one by one. 100 is what is just a factor that I need to optimize to get the best spreading, right? That's what we have. So we can do that. We can find some best factor in some funny way, but we're just providing a number. We just call it factor, which means a variable. And we can ask that variable as an extra input argument. So we need to say, if you want to have that function called, you need to give me whatever factor you think is best for the type of data that you provide. And the second thing is the 19. Of course, that's not a very nice way of doing things. So how can we get that range 19 in a nicer way? Well, it's actually quite easy because we know what 19 is. 19 is the number of columns. How do we get the number of columns? Number of columns, just make a variable of that name, and that is nothing but the data shape, and it's the first number of data shape is the rows in the array, and the second number with index 1 is the number of columns. So we have that. And how can we get a range of the number of columns? Well, we don't put that in here. Copy that out and we say, what do we call it? We call that the offset. That's the actual offset, and we calculate it as a range of not 19, but of whatever number of columns you have, right? Should go. So if we do arrange columns, we know we get from numbers from 0 to as many columns as you have. That's our offset, our default offset, and then whatever the factor is needs to be multiplied with this offset to give us the offset that we need in that plot. Execute the function, call the function. Oh, that gives an error. Why is there an error? Because the function definition says you need to give 2 arguments. But that's simple, separated by comma. We know what works best. It's 100 that worked best before. So if we do that, we get a nice plot of the data, each column separated from the other by a certain offset. And we can look and have a good impression of the whole data array or data set, which in this case is human EEG from some pediatric patient.